care about what is the right choice of n. Then maybe we can just think about multiple choices of n, right? And then the average, the estimates that we get with all of them, right? Now, to get this idea, I just put you here one simple example, right? Look at this guy here. Now, if I am at the particular, I am considering two different cases. One of them is n equal by 0. The other one is n equal by 2, right? Now, if I am in one particular state, right, I'm at this state, I can use, or I can collect one sample considering just the next time step, right? This is TD0, correct? So I would say I am in this state. Then I get one immediate reward plus the value of the next state, that is TD0 estimate, right? I can also do it by n equal by 2. So I go one step, two step, then I do it, right? Correct? Actually, one step, sorry, two step, three step, and then I go, right? So I can do it with two different choices of n for every single state, right? And then when I get both estimates or both samples, I average those samples, and then I use that one as my new sample. So you get my idea what I'm talking about the averaging, right? I'm at this time. I would say, OK, I go one step further. OK, I'm here. Now, TD0 already gives me a way to estimate or sample from this time, right? Whatever I collected as the reward plus the value of this time step, right? But maybe I want to go more. OK, I have this estimate. I have this, this sample. That's OK. I go one step more in time. Now, again, I am in a new time step. So if I want to use TD1 now, I would say, OK, the first reward plus the second reward plus the value of this state, right? OK. Anyone knows whether the previous sample was better or this one? Well, we don't know it, right? I mean, this guy tells us that we don't know it, right? Necessarily. So because of that, maybe I take that one, add it to this, I average them, right? And again, I go one more time, right? So one next time. Now, TD2 would tell me first one plus second one plus third reward plus the value of this time, right? I again average with this guy and keep on going, right? Up to where I want, right? So this is what I mean by averaging over time. Everybody sees what I'm doing, right? So maybe we can do this one. Now, the question that you might ask me is that why this is a good idea, okay? Now, if you consider that curve I showed you going down, right? So it says that when I keep on going in time, up to some point, I am improving, right? After some point, I am just making things worse, right? Now, if I don't know what that guy is, maybe I can look at everybody and average them out, right? Now, the good guy is there, the bad guys are there as well, but they average out. They are definitely better than the bad guys, right? And if the good guys are very low, then they are going to dominate the whole thing, right? So this is the idea that we can do. I mean, we can say that, OK, the good one is within these guys. So if I average that out, this might potentially dominate. If it does not dominate, at least it's going to improve as compared to the case that I just hit one particular n, right? So we do not have the exact idea which one is the best one. So basically, we just average everything forward, right? Now, one thing that you might say is that, OK, this is going to help us in the sense that we are not anymore focusing in one particular depth in time. So we are not thinking about one particular n. But at the end of the time, if you want to average, this means that I cannot go again towards the very end of my trajectory, right? Because I still need to compute the estimate or the sample of TDN, right, each time. And then this means that the last n guys, I should throw them away. Well, we can just get rid of that issue, but the idea of geometric weight. So what is the idea of geometric weight? At every single time, I am going to compute my sample return in this form, OK? Now, this might look a bit complicated, but once we open it up, you see what I'm doing, OK? No worries. Now, what I'm doing here, so you see 1 minus lambda here, right? Lambda is a number between 0 and 1, OK? Half, 0.2, anything that you want. And then this capital L is the length of my one particular point on the trajectory, Okay? Now, let's just start from time 0 and see what I am doing. Okay? Now, if I want to compute this gt at time 0, okay, first of all, set L equal by 0. L equal by 1. Set L equal by 1. This means that I am at the state S0. I go one time step forward. I am now at S1. L equals by 1. Okay? Now, can you tell me what is that, guy? Can you tell me? It's going to be, I'm going to have 1 minus lambda, right, times. This is mentioned from 0 to L minus 1. This is going to be just the guy 0, right? Lambda to power 0 is 1, right? So this is going to be gt 0, right? This is going to confuse you, so lambda equal by 0. Now, or gt lambda, sorry, it's not this guy, sorry. gt lambda. Gt lambda is 1 minus lambda gt 0 plus, what is the second term? Lambda, L is 1, gt 1, right? Correct? So, TD0 plus TD1 average by lambda, right? So this is obviously an average, right? Because 1 minus lambda plus lambda is 1, right? Everybody's clear, right? Okay. Now, here was L equal by 1. Let me do L equal by 2. gt lambda, what it will be? It's going to be 1 minus lambda. Then you help me write down the other things. So what is that summation? gt n starts from 0 to L minus 1, which is now 1, right? L is 2, 0 to 1. Then you have lambda to power 0 first. It's 1, so I'm not supposed to write anything. Then I should write gt 0 plus, what is the next term? Lambda gt 1, right? Plus, what is the last term? Lambda squared gt 2, right? Now, gt0, td0, td1, td2, right? Each of them is getting multiplied with one weight, right? Now, let's just compute the weights. If I just multiply 1 minus lambda with this whole thing, so 1 minus lambda going to show up here, so I can write down this one as 1 minus lambda gt0 plus, what's going to happen to this guy? So 1 minus lambda going to show up here, right? Correct? Right? Now, I multiply 1 minus lambda with lambda as well, so this is going to be lambda minus lambda squared, right? Everybody's clear? Now, add up the weights. 1 minus lambda plus lambda minus lambda squared is, so minus lambda going to cancel with lambda, right? 1 minus lambda squared plus lambda squared, 1. So these weights have always this property. It doesn't matter what L is. If you add up those weights, it's always 1, right? You see that, right? And what I am doing, I am computing an average of every guy in front of me, right? So I'm going to say I'm in time t, right? Then if I use TD0, then I'm going to get GT0, right? And then if I use TD1, then I'm going to get GT1. If I do TD2, I'm going to get GT2, and so on, right? I can compute all of them towards the very end, right? And then I average everybody in this trajectory, right? Now, this guy is getting me rid of the sample inefficiency problem. Can you say why? Because I can choose L as I wish, right? Right? If I am here at the beginning of the trajectory, I can just consider TD0, TD1, TD2 towards the very end, right? If I am somewhere very close to the end, then I can just take a few TDs, right? When I get exactly before the last state on the trajectory, I just use TD0, right? You see that, right? Everybody's clear? So this L here, this value L, the length that I'm specifying, I can choose it, right? And every single time I can choose the length that I have, right? So when I'm moving on my trajectory, every single time I would say, well, I can go at most, I don't know, length 5, right? Let me average everybody I have in front of me, right? But when I get to the very end, I would say, oh, I have just single time step left, right? So you see what we are doing, right? Everybody's clear? So the main idea here is like this. So I am taking, like, if you think in terms of the trajectory. So here is the state that you're starting from. You go to the next state, right? Now, when you get to the next state, you can already compute zero bootstrapping estimate, right? You can compute the sample of TD0, right? You give it the weight 1 minus lambda, right? This is this guy. 1 minus lambda GT0, right? Now you go one step further, right? You just go a bit deeper. So this is the second time step forward. Then you would say, okay, this is one guy, which was TD0. I have it already. Now I just skip this one. I get here. When I am here, again, I can estimate, or I can sample the return using TD1, right? I would say first return reward plus second reward plus the value of the second next guy, right? And then this is the TD1 estimate, and then I am going to just multiply it with 1 minus lambda times lambda, right? If I keep on going, if I go for TD2, then I am going to have first guy plus second guy plus the third guy plus estimate of this one, right? And I can multiply it with 1 minus lambda times lambda times lambda, right? Each time I'm going forward, I add 1 lambda, right, to that coefficient. You see it, right? And then if you keep on going towards the very end, this is the last guy on your trajectory, you're going to stop there, right? And then L is specified with the length that you had on your trajectory, right? Correct? Everybody sees that? Clear? Thumbs up? Yeah? I mean, you don't really communicate with me. I mean, you stopped, somehow we got detached. Yeah, I understand. I mean, the timing is not well for the course, but I hope that things are clear, right? Sounds very good. Okay, so this is helping us with the sample inefficiency. Basically, what we are doing, we say, like, at the very beginning, we can go very deep. When we get towards the end of the trajectory, we cannot go that deep. That's okay, right? We just take whatever we have at a single sample stage, right, in time. And if we do that, then this is essentially the idea of TD-Lambda algorithm. So TD-Lambda is basically lambda average. And by lambda average, I simply mean this guy, right? Lambda average of whatever you would do in different choices of n, right? So what here, you essentially start with this state. So when you are at state 0, you have TD0, right? Which is given by this state S1, right? You have TD1, which is given by state 2, right? S2. And you can keep on going till you have TDT, which is given by your last state, right? So you have all of them, you average them, right? So this is what I mean by line 6. So in line 6, it's not anymore easy for me to write it down. I do understand that it's a bit hard for you to imagine how exactly computations are going on, but you don't really need to think about the numbers here. You just think intuitively. Like here, you can compute, you can get one estimate when you look one step forward. If you look 2 steps forward, you can compute another estimate, and so on, right? You get all of them and you average them by some weights, right? Which are specified by lambda, right? And then again, you go forward. You go the second time. Again, at that time, of course, you do not have as much estimate as you had before. You have one less, right? because you are not going to have TDT anymore. You have TD0, TD1, TD2, till TDT minus 1, right? And if you keep on going, at the very end, you're going to have only TD0, right? Nothing more. Everybody's clear? Questions? But now, this guy is going to let us look at line 5. It is going to help us just go towards the end of trajectory, right? Because if I am at time t minus 1, well, I have only the TD0 estimate, right? I'm going to take that one. That's okay, right? Questions? No question? Everybody's clear? So this guy is what we call a TD-Lambda. So you can do it for value. I have given this guy for value. Obviously, you can do the same thing for action value, right? No need to just repeat that. OK, cool. So now, two things that you might pay attention to is what's going to happen if you set lambda equal by 0 and lambda equal by 1. OK? Let's put lambda equal by 0. Look at the board. If I set lambda equal by 0, what's going to happen in the first one? You see it here, right? If I put lambda equal by 0, what's going to be my sample? TD0, right? What about this one? What about this one? Again, TD0, right? So that lambda is going to show up anywhere after TD0, right? And when I said it's 0, everybody going to get 0, right? When lambda is 0, I have TD equal by, I have only TD0, right? So this means that lambda equal by 0 is basically TD0, right? Every single time you just look at the next guy, right? You don't go deep in time. Everybody's clear, right? Everybody's seeing it, right? Now, what's going to happen if I set lambda equal by 1? You are just taking the very last one, right? And if you are at 1, if you think of one single trajectory, whose very last state is a terminal state, what are you doing then? TDL, that's right, but I mean in that particular example where you have just your last state to be terminal state. What's going to happen? You're going to get, you start from very beginning, right? You just average TD0, TD1 till TD last guy. But TD last guy is 0 simply, right? So you're going to just collect this one. It's a sample return you get, right? For this one. For the next one, again, you do the same thing. You add this one, this one, this one towards the end. For the next one, again, like that. What is that one? That is Monte Carlo, right? Every single, when I put lambda equal by 1, if I think of the very last guy, like in my trajectory, look at it here. If that ST is a terminal state, what if I put lambda equal by 1, then what I am doing here at time 0, I don't care about any TD in between. I just collect R1 plus R2 plus R this guy till I get here, and then value of this one, which is 0, right? So what I am taking as a sample is sum of all of these rewards, right? If I go the next time, again, I am averaging with lambda equal by 1. This means that I do not care about any TD in between. I only care about the last TD, right? And the last TD is R2 plus R3, so on, RT, plus the value of this guy, which is 0 again, right? You see it, right? You're following, yes? OK, cool. So again, I am doing the same thing. So every single time, relying on the fact that the last guy is a terminal state, I am simply sampling by Monte Carlo approach, right? I'm just computing sample return by Monte Carlo. And this means that when lambda equals by 1, then I have eventually the Monte Carlo, right? So what you can say, if lambda is 0, then essentially you always compute your GT lambda in this form, right? Which is essentially TD0, next reward plus the sample return of the next state. And if lambda equals by 1, then, well, eventually you are just computing anything towards the end. and you are dropping the last guy, which assuming that that last guy is a terminal state, that value is always 0, meaning that what you have here is basically Monte Carlo, right? Everybody's clear? Questions? So what is happening now, you have a lambda value, and that lambda value can change between 0 and 1, right? If you start with 0, you're TD0. If you start to gradually increase it, you're getting from TD0 to Monte Carlo, right? So it's a better sort of, spectrum pacing as compared to the case where you have n, right? And you have also this property that you are not throwing away any sort of sample, right? So you are efficiently using the whole trajectory to update your estimates. So this is again the same thing as before. So here is TD0, here is TD1. And now, yeah, it might sound a bit confusing because we have TD/0/1, right? And this is where we have n. But at this point, from now on, you just throw away TDN because we're not going to use it, okay? I just defined TDN to define this one, okay? We're going to hopefully get rid of the whole thing today, and then we end up with one thing. You can just use that one, okay? But to get there, we need to get all of these troubles, right? So by TD, I'm showing it as an index now, and this lambda could be something between 0 and 1. If lambda is 0, then I am at the basic TD. If lambda is 1, then I am at Monte Carlo. And essentially now I am just continuously, moving between these two different cases. This is different from TDN, right? It was like 1 step, 2 step. It was quantized. Now you are continuously changing, right? Everybody's clear? Questions? No question? Okay, so now again, if you just do the same thing. So again, you have your environment, you fix the number you're using, you specify the exact value function, and then you start to estimate it using TD-Lambda. Then what you can see is that if you set lambda equal by 0, then you're going to, this is again error with against the step size alpha, then you're going to have this optimal value for the error. Now if you increase value of lambda, then this is going again to drop, and at some point again this is going to go up, right? And it's the same property as before, right? This lambda is not pretty much doing anything different as the case as n. Basically, the only difference that is happening here is that you are now within a very limited space, right? Everybody's clear, right? So again, there is a one specific choice of lambda, but then this change here is going to be smoother as compared to the other case, right? In the other case, it would be deeper because for every single n, you ignore any other TD estimate, right? But now you're averaging all of them, so it's going to reduce the convexity of this diagram. So you're going to have the same thing. Again, you're going to have a minimum against lambda. That minimum eventually happen depending on the number of episodes you're using at the point where you have the sweet point, like you have you have reduced biased enough, but you have not increased too much the variance, right? And then after that lambda, you are going to increase the variance. Questions? So now if you got no question, then let's just get to the more interesting part of this whole discussion. And the more interesting is that how we can really include it into a practical algorithm. Because what I'm doing right now, of course you have seen the algorithm for TD-Lambda, but at every single time, what I'm doing, I'm just looking towards the very end, right? I'm evaluating all TDs, right? I'm averaging them out, and then based on that, I am improving my estimate, right? I again go for the next time. I again look at everybody ahead of me. I just average their estimate, the estimates given by them. I update, right? And I keep on going like that. And this is a kind of exhausting approach, right? This is not really practical in time, right? You want to have some sort of online algorithm that every time you just do one single operation, that's it, you go forward, right? Now, to see that, let's first of all look at this diagram. And this diagram that you see are the weights of this averaging that we're doing, right? So look at this guy. This is, in this case, when I have only two terms, like my trajectory is very small. Then my first weight is 1 minus lambda. The second one is lambda, right? Say, for example, lambda is something like 0.2. Then this guy is 0.8. This guy is 0.2, right? Now, what's going to happen if I increase? This is going to be 0.8 as before. Then this guy is going to get smaller. It's 0.8 times 0.2, right? And then this last guy is 0.2 squared, right? So it's going to be 0.16, 0.04, right? Now, the thing that is going to happen when you look at this time, this is you are at the particular time t on your trajectory. Whatever you get with TD0, you're taking it by 1 minus lambda. The next guy, the weight of the next guy is reduced, right? The weight of the guy after is again reduced, right? So on, the weight of the last guy is the smallest one, right? And this is going to go down, right? Everybody's clear, right? What is happening? So when you are estimating here, what you can say that the next guy is having the high, like the estimate that I get out of the next guy is having the highest weight in my final update. But the one which I am considering to be at the very last of the trajectory is just contributing the less in this update, right? Okay, so now, you might ask me this question that, is there any specific intuition looking at these ways? And there is actually a very interesting question, because this is the whole idea of what we have in this section, supposedly, is what we call it credit assignment, right? So let's first talk about this one. So what I'm doing right now here, I am just removing all of these lambdas here that we have on the board, okay? I just make it simpler for you. What I can say that at every single time that I am, so I am in one particular point on my trajectory, I'm going to get the TD0, TD1, TD2, till the last TD I can compute, right? And then I average them with a bunch of weights, right? This WTN that you see, this guy here, is actually those weights which are dropping always, right? As you go forward in time, they are going to drop, right? And the thing that is happening here is that the first guy, as we said, like TD0, has the most weight, and the next guys are going to have less and less weights, right? What does it mean? It means that when okay, I'm going to look at the next state, and based on the next state, I'm going to decide, okay, I guess that I'm going to get this much of value, right? Because the next state is this, and based on my available estimate, I know, like I am here, I just go to the next state. In the next state, I get value 10, right? And then I just collected one reward, so I say, okay, I estimate the value of my current state is 11, right? Now, if I go steps forward, maybe the second step value is 6, right? And then I had collected 1. Now my update or my estimate is going to change, right? I say like 1 plus 1 plus 6 there is 8, right? Now, the question is that which of these two numbers is more valuable, 11 or 8? Yeah? Because my next state tells me, I mean, you start from here, you ended up there, you collected 1. Here on, you're supposed to get 10, right? The second next state is telling me like you started there, you just collected 1, another 1, this is 2, and from now on you're going to collect 6, right? So 8, right? Which one is more trustable? Now, natural thing that we do, we always look at the next state first, right? So if someone tells you, oh, do that, and you are going to get this much money, right? But you might know that, okay, if I get that money, if I keep on playing, I might lose, right? But this is a natural thing that we always give more priority to what we see next, right? We're relying more on what is right now happening as compared to what is supposed to happen in very, very far future, right? So you do not insure yourself for 100 years from now, right? But you insure yourself for your next trip that you're going, right? So this is the idea. The more you go in future, the less weight you would give to your estimate. And this makes sense from a kind of natural learning process that we have, right? When we want to find or evaluate our policy, we just play once and say, oh, we got a very good outcome, right? So because of that, this is a good policy, right? Well, if you keep on going in time, maybe you start to lose, right? But who knows? You always rely on that one. So what you're doing, you're giving more credit to the immediate reward that, or immediate observation that you do next to yourself. And this is the idea of credit assignment, because you could always bring up this question. The question is that, well, I am here. If I get immediate reward, which is very good, that's fine. But maybe in future I lose too much, right? And then how I can rely on what I see? Well, this approach, what we are doing here, or TD-Lambda, what it's doing, is giving it's not ignoring everything in future, it's still taking that into account, but the more you go in future is giving less weight, which is somehow natural given the way that we play games or we interact with an environment, right? So what we are doing, we are essentially assigning credit to the kind of estimate based on the observation that we are going to do in future. And every time that go forward, since we are getting more far away from our current state, we are going to just give it less weights, right? Less credit, right? So a normal person is, for you, is the one who is saying, thinking about the the salary of the next 3 months, right? A person who is just losing too much salary because he is thinking in 2 years he is supposed to get a huge reward is not very rational to us, right? And this is the same thing that we're doing here, right? Everybody's clear, right? So this is how you can think of it. So you are at the particular state S, ST, right? And then you're going to have all these states towards the very end, right? And each time you're collecting one reward, and you have one estimate for the guy in future, right? So you would say, okay, the estimate given by my observation here is more credible as compared to the estimate that I'm going to give after seeing this guy, and so on towards the end, right? And this makes more sense, right? But clear? Questions? No question? Okay, so now, that's pretty much this interpretation. The only thing that is left that we need to do is to just find out if there is a way that instead of looking towards the future, in every single time I can just do my update and I don't look at the future to update, right? Because right now I need to just get this estimate plus the next estimate. I average all of them, and once I average them, this is going to be my estimate for, or my update for this time, right? Now I go to the next time step. Again, I need to repeat the same thing and so on. This is, as I said, very exhausting. Is there a way to do it online or not? Okay? Now, there is actually a very simple way to do it online, and this is what is the final goal of this whole discussion here, that you just understand this algorithm. Now, from now on, I mean, if you had any trouble following details there, you can just throw it away. The only thing that I want you to keep in mind is basically this one. So is that when you are doing TD-Lambda in one particular state, right, you can just talk about the future based on your trajectory, right? So your future is like the immediate reward plus estimate of the next one, right? 2 immediate rewards plus the estimate of the next one, and so on, right? You have all of them, and you combine them. And how you combine them, you rely more on the next guy as compared to the second next guy, third next guy, and so on, right? Right? You rely more. And for weighting that, you have a solution, right? Now, the thing that we want to do, we want to see if there is a way that I can just update here without taking into account whatever is in the future, right? So I just start from beginning of my trajectory. I update, I go ahead, I update again. I do that, and I don't really need to rely on the future so much, right? I want to see whether I can do it. This makes more sense. This is what is going to end up us with the algorithms that we know, like SARSA and Q-learning. So